Hello. Oh, God. Hey, guys. We're just going to get started. So if you could make sure you can see the screen. I don't know if there's one. Oh, there's one over there, too. Sweet. Hey. Everyone, that's getting food right now. We're just getting started. If you could keep it down. Thanks. Cool. All right. So welcome, everyone. My name's Kyle Holzinger. I'll be your host for this evening. Please feel free to grab some food over there, drinks if you're hungry and thirsty. We got a packed night ahead of us. The Wi-Fi password is, oh man, I have this. It is stock with a capital S and then 10118 in case you guys don't have it yet. And if you need to use any of the restrooms, they are back there. All right. Before we get started, I'd like to give a big shout out to Shutterstock and Jessica for hosting us. Thank you very much. I don't know where Jessica is. Round of applause. And also for providing us with awesome food and recording the event and all that good jazz. All right, let's jump into this. So we have three really great talks today. We'll start off with Shweta is going to share how Shutterstock leverages Knock and Puppeteer to continuously improve the quality and relevancy of their web platform. And next we'll hear from Scott about powering micro front ends using their middle tier application called FES, or front end service. And lastly, Carlos is going to give us a presentation on building lightweight microservices using Hydra, a tool that leverages Redis for building distributed computing applications. I'm really looking forward to these great talks. Shweta, I'll let you take it away.
Good evening, everyone. My name is Shweta. Welcome to Shutterstock. Today, I'm going to talk to you about ways with which we can do reliable integration testing for verifying our front-end web applications. A little bit. Oh, sorry. A little bit about myself. I'm a senior software development engineer here at Shutterstock. I joined the company in November 2016. Been here for about 2.5 years now. My background is telecommunications and computer sciences. I joined the company and I started working with the public API team that works on delivering our public API interface. Very recently, I moved to front-end web application development team with a view to reassess and enhance our current automation test suite. This is the agenda for my talk today. We'll be quickly going over some concepts and locking down key definitions, followed by establishing the problem definition, the research that we did to solve the problem, and finally the solution and the wins. So let's start. Test pyramid. This is one of the most common strategies that is adopted by most teams in implementing their test framework. Test pyramid basically tells you how you can build your test strategy and says that the granular tests or the tests that are close to your application should sit at the base of the pyramid. The layers of the pyramid change and can be named differently, but the spirit of the pyramid is that a heavy-duty testing should happen at the base layers, and as you go up the pyramid, your test count should become fewer, with your end-to-end tests really being a lightweight test suite. To go into some key definitions of these layers, the first up is unit test. As the name suggests, it verifies the smallest testable piece of code. Typically, it is a function. These are white box tests with fixed inputs and deterministic outputs. And as such, these tests are very fast, and they should always pass. Sometimes unit tests get ignored. People are not very conscious about writing a lot of unit tests. But I think unit tests not only give an insight into the quality metrics of your code, they're also important because they're self-documenting. If you look at a unit test, you would already know what a function does and how it behaves. Also, when a new developer joins the team, having a high code coverage gives them confidence that they can write newer features without risking a lot of regression. So the more unit tests you have, the stronger your base is, and stronger the base, the better the foundation of your test strategy is. The next in the layer are integration tests. These tests verify your application as a whole while mocking or stubbing out any of the external dependencies. This allows you to test your application in isolation. And again, because you are controlling the external dependencies, you can really write deterministic tests at this level. The next and the tip of the pyramid are these end-to-end tests. End-to-end tests run against a deployed instance of your application. They are black box tests. They also aim to do some additional verification aside from just verifying how your application behaves. For example, say you have a page that accepts users' credit card information and then does some financial processing. These tests then become your SOX test, which get verified at the end-to-end layer. These tests not only verify whether the input is right and the user sees the next page correctly. You might do some additional checks, such as is the audit trail generated properly, or is the business getting the data reported correctly, etc. But because these tests run on a deployed instance and they depend on other deployed services, they are therefore vulnerable. And as such, when any of the dependent services of your application go down, your tests can start failing. In some cases, the tests then get labeled as flaky tests. And I should tell you, as an SDET, I really hate that term. So with the definitions locked down, let's now look at the problem that we're trying to solve. At Shutterstock, our front-end web application is a collusion of various microservices. The front-end application calls each of these services RESTfully, orchestrates the data as needed, and then renders it on the page. So as a developer who's writing a feature, or as a person who's testing this front-end application, always expecting that these 20 to 30 services are up and running in a pre-production environment at all times seems a little bit optimistic. So we want to write reliable tests. We want to write reliable controlled tests where we can actually control our input and get deterministic results. But at the same time, we don't want these tests to be as myopic as unit tests. We want them to do more. We want them to exercise users' flow and some of the complex test scenarios. So therefore, the objective of our problem becomes, we want to write tests that are reliable, like unit tests, but we also want them to exercise complex front-end user flows and trust the test and trust the quality of the tests. So with this objective in mind, we embarked on a journey. We first began by locking down the knowns. So to implement any test framework, we need a test runner, and we need an assertion library. At Shutterstock, we used Mocha and Chai previously, and all of us here are familiar with it, so we decided to stick with those. To introduce reliability, we needed our front-end server. We needed to control the external dependencies of a front-end server. And because our front-end talks to the services RESTfully, NOC was a great candidate to capture those HTTP requests made by the server and mock them. So we locked down these three knowns. We said we needed Mocha, we needed Chai, and we needed NOC. But we also had the next aspect of our objective to solve, which is writing complex test scenarios. And then we started looking for a framework that would allow us to do that. The first framework that we experimented with was Nightwatch. And as soon as we plugged in Nightwatch with NOC, we realized it was rather silly, because NOC was able to intercept the requests made by the framework to Selenium, because Nightwatch is a Selenium-based framework. It was not really able to intercept and override requests that Selenium ultimately made to the external services. So this did not solve our requirements at all. The next candidate we started looking at was Cheerio. And while Cheerio integrated well with NOC, at the end of the day, it is just a DOM parser. So when we wanted to do complex operations like clicking on a button or some AJAX operations behind the scenes, Cheerio didn't let us do that. So that didn't serve our purpose either. Then we stumbled on Zombie.js, which came close to solving our problem. Zombie.js has a good API library. It integrated well with Mocha, Chai, and NOC, and it allowed us to write complex tests. But there came a problem. Our front-end application, the way it talks to the external services, it doesn't just do that from the server side. We have calls made to external services from our browser as well. And Zombie.js didn't give us any support to intercept and override those calls. So then we started looking at other options like Casper and Phantom. And then I found that the Phantom.js's author had tweeted that he's deprecating Phantom.js in interest of Puppeteer. And that's how we found Puppeteer. Puppeteer is a Node API written by Google that lets you talk to Chrome or Chromium browsers using DevTool protocols. Because it is backed by Google, there's some credibility to it already. It has great documentation, and it had a rich API support. So it did meet our requirements. And as soon as we wrote a small POC, it just took us less than 30 minutes to build a small POC, and it integrated really well with the other 3 nodes, which was Mocha, Chai, and Knock. So then this became the toolkit of our choice. So after all this journey, our solution then became a composition of Mocha, Knock, Chai, and Puppeteer, and then that became our integration test toolkit for the front-end web platform. Let's now go a little bit into each of these components, especially Knock and Puppeteer. Like I said, Knock allows you to intercept HTTP calls that are made by your application. Where it is especially helpful is that because you're looking at your requests and overriding the response, you can really start doing some niche testing. For example, what if your service suddenly starts returning 500? Or what if your service crashes in the middle of your application's run? You want to test these scenarios, and with Knock's HTTP fixtures, we can do that. When we are designing the tests for the first time using Knock, we run them in the record mode. This comes with Knock for free. In the record mode, Knock intercepts the requests and saves them as fixture files. Now, when we are running these tests on our CI, we run them in the play mode, where these fixtures are loaded. And if Knock intercepts a request, it looks for a matching fixture. If it finds one, it overrides with the response it has seen in the fixture file. So with Knock, we were able to successfully intercept and override all our server-side calls and ensure that our application testing was reliable. But like I said, what about the calls made by browser? This is where Puppeteer's request interceptor comes in. Puppeteer's request interceptor behaves much similarly to how Knock works. It lets you look at the requests that are made by the browser and also override the responses. Some of the key ways with which we use this was to control the test scope. For example, some tests didn't need all the assets on the page to be loaded. And as such, we were able to block those unnecessary assets using this request interceptor. We were also able to override requests that were too slow and had nothing to do with the tests that we were writing at that point. So we were able to override and eliminate the slowness there. And finally, we were able to implement the logic to wait for XHR requests. As this graph shows, after implementing the request interceptor from Puppeteer, we saw a 30% runtime improvement in our tests. So then this becomes our test workflow. I'm sorry about the zoom size, but the upper part of the workflow shows the scenario that happens when a developer writes tests for the first time. The Mocha starts this application locally, and the test launches the browser. If we are running the tests in the record mode, then all the calls that are made by Knock and by Puppeteer's and by the front-end application are recorded by Knock in Puppeteer and are saved as fixture files. The lower part of the workflow is what gets executed on our CI, where we load the fixtures, we test the scenarios that we want to test, do our assertions, and then finally shut down the browser and close the application. So now going into some of the other key features of Puppeteer that we liked. Aside from the awesome request interception that it provides us, we really like the option of slow-mo. Slow-mo, as the name suggests, lets you slow down the operations that are made by Puppeteer by specified milliseconds. This was especially helpful to us in simulating some rather unique user scenarios, where what if a user types in really very slowly in an input field? How is your component behaving in that situation? Or what if somebody is hitting the submit button too fast? So slow-mo lets you configure that and generate some of those edge case scenarios. The next key feature of Puppeteer, which we are still exploring, but we see a lot of promise in, is the ability to capture timeline trace. Because Puppeteer talks to the browser over the DevTool protocols, by just adding these 4 lines of code, you're able to capture the timeline trace and then inspect these traces by uploading them on Chrome's trace tool. This lets you understand your application's performance very early on. The other features of Puppeteer that we really liked are that the browser can be started and shut down in a headless and in non-headless mode. So when our developers are designing tests for the first time, they typically use the non-headless mode, so then you can see the browser come up and go down and design tests. The other feature of Puppeteer that is especially helpful is the ability to take screenshots and PDFs. When a test fails, you typically want to know at what was the state of the page when the test failed. And having these screenshots helps in that. And finally, the ability to use debugger in the browser. With Puppeteer, you can set up debug points in your tests, and then set up breakpoints in your tests, and then step through your tests. And you can see how the browser interacts with each step. So with all these features, naturally there were wins, and I'm really excited to share those with you. The first win was the reliability. After implementing Puppeteer at our integration test layer, we saw a 96% pass rate. The missing 4% was when we were introducing it in the beginning, so we still had some kinks to solve. So it did solve the first part of our objective, reliability. The second biggest win was that it is 78% faster than any Selenium-based framework. To give you some example, we have 243 tests, which each of the tests executes a complex user scenario that run in about 4 minutes. We extrapolated these numbers with a Selenium-based framework like Nightwatch, and we estimate it would take anywhere between 14 to 15 minutes to run those scenarios. So with this was again a very big win for us. So not only have we achieved reliability, we have achieved the ability to write really complex tests at a much lower level in the pyramid. The next benefit is the feedback. Because the way our tests run, we start our application locally. And on a pull request, these run in parallel with the unit tests and our ESLint. So therefore, a developer gets to know the health of his code within the first 8 minutes of creating a pull request. This allows us to develop faster, be more agile, and it also helps us evolve and have a shift-left test mentality. So the next big win for us was sort of building custom parallelization. A little backstory here. Knock by default does not support parallelization. Mocha by default does not support parallelization. And because Knock hijacks the global HTTP object, integrating it with any other parallelization tool turned out to be complicated. So what we ended up doing was implementing a simple parallelization. We basically started launching each Mocha process for each test file in individual threads. And by doing this simple parallelization, we were able to achieve a 50% improvement in our runtime, in our test runtime. And the last key result that we were really thrilled about was early insight into performance. Because we capture the requests both from the server side and the browser that are made to external services, we can test our front-end app in isolation. We are then able to see and ask critical questions like, does my front-end application really need to call these 50 different services to render this small component? Or we can ask questions like, do I really need the whole response body from the service to render this small piece of data? And by getting insight into that sort of information has really allowed us to inject performance very early on while we are developing our features. Aside from this, some other minor wins that were really beneficial to us, one of which was the ability to inspect server logs as the test was running and look for any warnings. For example, if we started seeing a lot of prop type value missing warnings, we started alerting the developers on their pull requests, hey, something is missing somewhere. So because everything happens in one instance, the application is started, the browser runs, and your assertions happen all together, you can basically get a full insight into the whole bandwidth of your application. Naturally, these results are not enough. We want to grow and evolve, and we want to try out newer things as well. So we are using Knock today for our request interception, but on Thursday we found out that Netflix has released Poly.js, which is similar to Knock, as I understand, and allows you to override HTTP requests. So that's going to be our next experiment. We're going to try and see how Poly fits into our integration test toolkit. And the next innovation that we're going to try is the ability to use an elastic cloud interface. Today, our tests start and stop the browser, which still takes which still adds certain extra time to your test runs. If we are able to use browserless or Chromeless, that is then able to provide a pool of browsers, we expect to save some more time in the time taken by tests to run. So that was the journey of how we reached our integration test toolkit for front-end application, how it really changed the way we do testing. And it also started, because all of these toolkits are JavaScript libraries, which is what most of our developers here are comfortable with, it was really easy for us to get adoption on it. We introduced this toolkit in February, and we already have over 300 complex test scenarios being written, and it's growing. This whole journey was done and developed together with all of us here at Shutterstock, but I do want to call out our sponsor, Karen, she's right there, for motivating us in building this, and Karan Shahani, who is a senior software engineer in Montreal, who collaborated with us to make this tool. With this, I conclude my presentation, and I'm happy to take questions. Yeah, that's something we do manually right now, because it's really, sometimes you need all that data to build that component. So right now it's a manual process. As the fixture files get generated and saved, they get committed to our repository. So there are people who review it, and then that's where we start asking those questions. That's it. Thank you, guys.
All right, thank you so much. I believe Scott is up next. There he is. You know what I'll do? Sorry, big. All right, hello. Sorry. Sorry, my name is Scott. I'm a senior software engineer at Smartling. Smartling is a company on a mission to make translation easy. And I'm going to talk to you today about how we orchestrate micro front ends at Smartling. So just a little background on the problem we're solving. We moved to a microservice architecture, but we still had a front-end monolith. So some of the problems we were having was development's difficult,
large and complex. We have a large and complex code-based, slow CI and continuous delivery, and we had to redeploy the entire application on every update. So we set out to fix this, and our design goals were we wanted to create small, contained, single-page apps. We wanted it to be technology stack agnostic. SmartLing at the time was fully Backbone and Marionette, and we wanted a way to introduce React without having to rewrite the entire application. We also needed quick release cycles, simplified development, built-in security, and we wanted to structure our teams around functional business domains. So what we did is we started looking towards the microservice principles, and we wanted to use them to apply to micro front ends on the front end. So what are micro front ends? You can think of it as a web app that's a composition of features which are owned by independent teams. So single page app plus standalone components deployed independently of one another. And teams develop end-to-end from database to user interface. So with these composable UIs and cross-functional teams, I kind of tried to outline on this page how ownership might break down. So team product owns the product detail page on this fictitious e-commerce website. Team search owns the search box and the search results. And team order owns the mini cart and the order button. So it sounds nice, but we need to figure out a way to make this actually happen. So that's why I'm here to talk to you guys about micro front end orchestration. So since the micro front ends give us a way to reimagine how we think about code and dev teams, but they don't really discuss an outline of how we should orchestrate this. So some of the concerns that we have is we need to be able to determine what front end application to load for a given URL, determine what other front end code we need to load in order to facilitate page composition, and we need to be allowed to we need a way that we're allowed to make changes to our components without breaking things, but also without totally tightly coupling everything. So what we realized is we wanted to apply a microservice orchestration pattern to front end development. So I have on the screen an overview of essentially a standard microservice design pattern. And here the microservices are orchestrated by tools like Hydra, which I'm excited to hear more about later. And the other one that we use Netflix API Gateway and Eureka, if you prefer Java. And it also requires an identity provider. It could be something like OAuth or OpenID Connect. At SmartLing, we use Keycloak. It's an OpenID Connect-based IDP. It's open source. It also supports SAML if that's your thing, but it's a little complicated. And so anyway, so the key components besides the IDP of a microservice architecture are service registration and discovery. So where's the service located and what requests can it handle? And the API gateway, which sits in front of the services and dynamically routes requests based on the data in the service registry. So for micro front ends, we wanted to apply some of the same similar concepts. So you could sort of think about it as like a Hydra or an API gateway plus Eureka for front end assets. So we changed some of the terms a little bit here, but essentially instead of a service registry, you have an asset registry. So this facilitates registration and discovery. So where are the front end assets located and what requests can it handle? And we have this dynamic router which sits in front of our micro front ends and routes requests dynamically based on the data in the asset registry. So you can think of it lightly as, based on the incoming URL, which single page app should I render? And so dynamic routes, what we're talking about here is also very similar to microservices, where with services, if these were services instead of applications, we'd be saying, all right, the first part of this URL is telling us which service should be handling the request, and maybe some data attributes in the middle, and then the final endpoint. And we're doing the same thing here. We're trying to say, instead of writing server-side code that says, when you hit the order page or the product page, we are going to load this set of JavaScript, and we're going to load this set of CSS, and we're going to show it on the page. What we want to do is have our front-end applications tell the front-end service what JavaScript to load for a given URL. So you can kind of think of it as like dynamic routing for asset requests. So I have just a little example here. So in order to facilitate this, what we did is we came up with this idea called modules. And modules are just a logical grouping of pages. And they're dedicated to a specific functional area. So for example, in the e-commerce world, you could have product pages, checkout, and search. And they're declared by a JSON manifest that lives in the Git repo for each of the modules' code. So here's a sample of what a module manifest might look like. Each one has a unique identifier, a version. We use the semver major of these modules, or of the code in, like, say, the package JSON here, but we're duplicating it because this is actually going to publish publicly. And we have a list of pages that can be handled by this module. So this one's an example of products. Here's a possible order example where we've got a checkout page and a cart page. And one of the interesting things on this one is we've actually developed the front-end service to support front ends where the front end wants to handle routing. So things like React Router. So what you can see here is we have for the checkout section pages, we have that we've said client routing is true. And what that does is it tells front-end service that when a request comes in for a URL like this, the express router is going to handle the top part where it's determining which module to find, render the single page app, and then delegate the rest of the URL to React Router. And similarly with our search service, this one doesn't have a list of pages, this just is one page, and or one front-end application. And all of the routing is delegated completely to the front end. So this is what it looks like when a request comes into front-end service. So you see we get this request for a project page. So we're going to load the products module. We're going to locate the definition of the page being requested. And we're going to render an HTML view with references to the assets we need in order for the front-end application to render. So this is great, but we also need to be able to change these things with continuous integration and delivery. So how do we determine which version of a page we're going to load? So here's the way that we do that. Each front-end service has built into it a module registry. The module registry uses a Redis hash to track the current version that should be rendered for a module. And we have command line tools for local development and continuous integration and delivery servers that can update this information. And we provide RESTful endpoints, also secured with Keycloak, that allow you to manage the registry, either from CI or to be able to get a list of the modules that are in the system in any given environment. So here's how the CI flow looks for a module. So we do everything with pull requests on GitHub. And what we do then is our CI server is watching for a pull request to be merged to master. And after the front end is built and the test pass, we're going to upload the assets to S3. That's what we use as the back end for our content delivery network. We're going to activate that revision on front end service stage. We're going to then wait for automated UI tests, user acceptance testing, manual verification, whatever it is that needs to be done. And we'll wait for the developer to approve. When the developer approves, we're going to activate that revision on production. So one of the cool things here, because we're using this module manager, is that stage and prod deploys are like crazy fast. So I included a screenshot here from one of our CI builds for one of our modules. And you're looking at sub-second times to deploy stage and prod after everything's built. So it's pretty cool. Just wanted to show you, there's nothing crazy magical going on behind the scenes here in terms of uploading. we're just S3 syncing our built application. The important part here is, so front end is just the bucket name. But then what we're doing is we're packaging these in a logical directory structure where we're saying the top level is the module name, and the next one is the git commit hash for the version on master that just was published. And then deploying to stage is simple. We provide the script to the CI server, which just says front end service deploy. We tell it which environment to deploy to, which module to deploy, and which revision to deploy. And this has some safety checks built into it. So what's going to happen, and part of the reason we publish the manifest with the content, is that's actually going to trigger the front-end service to go out to the content delivery network, download the manifest for the revision we're trying to activate, and validate it. So we do JSON schema validation, but we also are going to check to make sure that all of the pages that the application's looking for are reachable. And if the checks pass, we're going to activate the module version. Same for prod. So yay, now we can deploy single-page apps, but what about the components? Right, so we're back on this product detail page, and so far we solved the problem of how we deliver the current version of a single-page app. But we need to extend this page to be composable. Right, so with micro front-end ideas, so with micro front ends, the idea is like we're thinking of the DOM as the API, right? So the developers of the product detail page have decided that they want, the search service to provide the search box. They need the order service to provide the mini cart, and they need the order service to also provide the add to cart button. So what's missing from this picture is how do we actually load the code that is behind these buttons? So what we did is we extended the manifest so that modules can publish pages, but they can also now publish individual components. And these components can be reused on other pages, either within the same module or other modules. So here we have the mini cart and the add to cart button being published. The search module is publishing the search box. And then here back on the products page, we see that we've updated the dependencies of our detail page to say that it needs those 3 components and the Semver major component version that it's been tested to work with. And then we've extended our module registry to also support components. So this way, when we do the upload, we can actually break out the current version. So we can always stick with the major Semver of like version 1, version 2, and then people who are consuming these can update them as necessary. But we can also release, minor features or bug fixes without the other teams having to go back and like update their code to consume the latest version of ours. And components are delivered from the content delivery network, just like our module pages. All right, so we're back here. So now we're going to do what we did before. We're going to load the products module. We're going to locate the definition of the page. And we're going to see that this page has dependencies. So we're going to load the dependencies, and we're going to create a dependency graph. And then we're going to render an HTML view that references the assets needed to render the front-end application. So you can kind of see what that might look like here. So some of the benefits of this are we're leveraging HTTP2 to efficiently deliver each component separately. And since we're independently versioning, we're going to get high cache hits. And most of this is going to be delivered from local cache. And we're also using Webpack code splitting to further optimize lazy loading of component code until actual interaction. All right, so security. So just like our microservices rely on Keycloak for security, so does front-end service. So front-end service manages authentication and authorization for our micro front-ends. We manage the session, the SSO JSON web tokens, and we use a Keycloak Connect, which is Express middleware, based security on all of our routes. And then we wanted to take this a step further. And what we do is we actually allow our module authors to define access control for pages in the application. So here's a little snippet from a manifest of a specific page. And it's specifying that in order to view this invoices view, the user has to either have this specific role, it could be a list of roles, which, it's a greedy match, so whichever matches first you're gonna get, and a list of permissions the user has to have in order to be able to view it. So again, we're sort of putting some control of the security into the hands of the front-end developers without having them actually have to manage the security rules. So a front-end service can take action if there's an ACL violation, can either do an HTTP 403 or for security reasons maybe a 404. And and as I was saying, it's taking care of all of the interaction with the SSO server for the front ends. So the front ends themselves don't have to be concerned with authorization. Either you're authorized or not. All right. So just to summarize what we built. So front-end service is a composition of a dynamic router. That's what allows us to route traffic to the appropriate single-page app. The module definitions. So these keep code contained, and code inside of a module is completely tech stack agnostic. The module and component manager. So these facilitate composable pages and keep deployments fast, sub-second, and decoupled. And security, so we leveraged our existing identity provider that we'd put in place when we moved to microservices to facilitate micro front-end development. And the last thing is we stuck to our micro principles. So this is just, I just put this in here because sometimes when you're developing something new like this, you get the idea that it's like, well, but maybe you should do this too, or maybe you should do that. And what we wanted to do is keep this Express application completely focused on request routing and module management. There's no isomorphic rendering, and there's no coupling between the front-end service and the micro front-ends it's rendering. It doesn't have to know anything about them besides what's in their manifest. And that's it. So thanks. I just wanted to thank Smartling, Shutterstock, and Node.js New York City, and special thanks to Keith and Steve Armstrong from Smartling. And we have some time if anyone has questions. Yes. That's a good question. It was a timeline from when we got the idea to production. It probably took us a few months to build out the solution. But one of the things that we did is the legacy system that we were replacing with the monolithic dashboard. We didn't just tear it down. What we did is we used routing rules that you could do in, say, AWS application load balancers or in Nginx to say that all requests under a new /app prefix that we came up for this stuff would go to this new front-end service, and the old requests would go to the legacy service. So what that allowed us to do was stand up this service with nothing on it, and then as front-end code could be pulled out of the monolith and put into this, it would slowly become the service receiving the majority of the traffic. Yes. Yes. Performance concerns. So the question was about performance concerns if we're using two different technologies. Yes and no. We did do there was some stuff that we couldn't dive into in a good amount of time here about how we're doing it. One of the things we're doing is we're actually using Polymer web components to isolate the code. So they're all rendering into a shadow DOM. But in terms of performance, there are ways that the components can actually have dependencies on other components, so that we could say, some specific version of a front end technology should be loaded by the front end service and cached separately. So there could be a little overhead with that, but it's not terrible. Yeah. So also, uh, so the micro front end uh, goal for that is that you should be using the DOM, and for anything, so like when I was showing the example of the add to cart button with the SKU in it, so the idea is that the consumer application should be providing data, providing attributes to, essentially that becomes the API. For something more complex, like needing to listen for like a pop-up close or something, use native browser events. All right. Thank you, everyone.
Yeah, that one's up there, so we're all good. Just that was surprising. Cool. You want to change the sound real quick, just so that works too? Just go to a different space or something. Okay, cool. Yeah, just go to assistant preferences. That's it. And you want it? Cool. I hope it works.
works. Okay. So welcome and thank you for attending this talk. Just a little bit about me. My name is Carlos Justiniano. I've had the pleasure of speaking here on several occasions, I guess, over the past 2 years. So some of you may recognize some of the material here. So I've done some pretty cool things during my career. You can find out more about me at cjust.me, and feel free to contact on me on Twitter and GitHub. So a few words about this presentation. This presentation is a condensed version of the presentation that I delivered at RedisConf 18 last April. So if you're interested in actually seeing the full presentation, you can see it at the Redis Labs channel on YouTube. There's also a related blog post if you'd rather just kind of read the details. There's more detail in the blog post, actually. So before we dive in, I'd like to quickly clarify what I mean by lightweight microservices. Light on external complexity and dependencies, meaning microservices which limit the number of external infrastructure dependencies. So not light as in limited. So microservices which are not limited in what they can do. So as I said earlier, I'm with Flywheel Sports. Flywheel was founded in 2010 here in New York City as an indoor stadium cycling studio. Our fitness programs feature high-energy workouts that will challenge even the most seasoned athletes. A cool thing that we do is we add sensors and microcontrollers to our bikes in order to track performance metrics. So we've been doing IoT for the past 8 years. We have roughly 1,200 employees across the country and 42 studios across the US, and we currently opened a new studio in Denver. So last summer, we prepared to launch our Fly Anywhere platform, which allows our customers to ride at home using our nationwide live video streaming service. How cool is that? Now, while we're not the first movers in this space, we are aggressively innovating. So, guess you guys can't hear the audio? Yep. Yeah, audio's not coming out, but got some video. So basically, this is the video that we released on social media that introduces the Fly Anywhere bike. You could actually broadcast to a large screen TV in your home, and it's got probably, I think it's the first Bluetooth enabled bike. So we'll move through this. Since you can't really hear it, we'll get back to some of that. So we're proud of our bike tech and our nationwide launch of Fly Anywhere, and pleased that we did this while embracing microservices and Redis. Although things did not start out that way. Just over 2 years ago, we started thinking about embracing microservices. After all, how hard could it be? I'll let you soak in this slide. Pat yourself on the back if you're familiar with each of these terms. If you're like the rest of us, some of those terms are still on your checklist to investigate. Now, you don't need to know all of this to build microservices, but they are important tools and concepts. So, there was a lot to consider, and unfortunately, we were also a small team with limited resources. That's 3 strikes if you're counting. Experts will tell you that small teams should not embrace microservices. One reason is that the microservices approach adds to the busy workload that many developers already have. There's a lot more to consider when embracing microservices, such as how services will work together, be monitored, debugged, and how their data sources will be organized. So a core challenge is that there's much to learn, which amounts to a lot of study time for an already busy team. So these were certainly concerns for us. We were also well aware of the great solutions large companies have developed and open sourced. However, even those gifts from the gods comes with steep learning curves. So a reality check was in order. We're not Netflix. and chances are you're not either. Naturally, if you are Netflix, then you have Netflix-sized problems which require extensive engineering by large teams. Given our size, development budget, and real business priorities, we needed to right-size a solution. We needed something small and robust enough to quickly get us started, while affording us a runway so we could later embrace other solutions as needed. So we started by assembling a checklist of features we felt we needed. If you already work with microservices, then this list is quite familiar. One of our most important concerns was that, or rather goals, it was that we had that an ideal solution had to be simple to use by less experienced developers, ideally implemented as a single package import. So I've been working with Redis for some time. Along the way, as I considered our checklist, I decided to take a closer look at Redis. I started seeing Redis as a sort of distributed computing glue. It looked like Redis could be used to bind and unify microservices. Each microservice binds to a shared Redis cluster. Presence is maintained by key and expiration. Inter-process communication via pub/sub. Routes placed in set stores. But was it possible? Microservice features using a single infrastructure dependency? We thought so. So we built an internal library called Hydra. The name Hydra seemed ideal because the service type often has multiple instances working together as a larger beast. On the right side is a list of features we were able to support. By the way, you'll be hearing the name Hydra a lot in this presentation because I'll use Hydra as a practical example of how Redis can be leveraged to build microservices. But you don't need Hydra. I hope that the takeaway here will be the ideas and how they might apply to your own version of a similar library or tool and across languages, not just Node, for example. Let's take a closer look. Here we see 3 microservices, each with a Hydra module which connects to Redis. In this model, most microservices don't communicate with Redis directly. Rather, the underlying Hydra module proxies to Redis. Another point about this diagram is that Redis is just another module, just like the ones shown in green. Hydra is only shown in blue at the bottom to illustrate its presence and connection to Redis. Here is a scaled-down view of Hydra as a JavaScript class. There are actually 36 member functions in total, but this snapshot provides a sense of our abstractions. So Hydra, with its single module import and fairly simple class methods, allowed us to chisel away at our monoliths and start building our Fly Anywhere platform as a collection of microservices powered by Redis. Fast forward 9 months, Fly Anywhere was already doing well, and Hydra was actually working really well for us. And so we felt that it would be useful to others. So on November 7, 2016, at the Smithsonian Museum of the American Indian in downtown, we open sourced Hydra on stage at the Empire Node Conference. I demoed Hydra running in a cluster of Raspberry Pis. My point in building the cluster was to reinforce the notion of a lightweight microservice library. In fact, light enough to run on $5 Raspberry Pi Zeros. Here's a close-up view of the cluster. It consists of 8 computers, 7 of which are Raspberry Pis, and 1 of which is an Arduino-based microcontroller. Each of the Pis are running Hydra-enabled microservices using Node 6.5. In total, the cluster contains 16 CPU cores. In order to further add context to this presentation, I'll briefly show you Hydra in action. Then we'll look under the hood to see how Hydra leverages Redis to form a lightweight microservices library. We'll drop down to the command line and launch a Docker Swarm cluster consisting of a dozen or so services. Some of the core services include Neo4j, MongoDB, and Redis. The rest are Hydra-enabled microservices. One of the services we'll use is called Hydra Router, which is a dynamic service-aware router. I'll wait for that to finish. So this is the Docker stack, if you're familiar with Docker. So the end of the process is basically a URL that can be launched to view the dashboard. There it is. So next we'll launch the dashboard via the URL that's provided. Here we see the Hydro Router dashboard. If we scroll the page, we see all of the services we just launched. So we can filter the services by name. And here we see that Hydro Router is itself a service, also listed on its own dashboard. If we look closely, we can see that the host name and instance ID match the text above the input box. So it shows that this particular instance is also the instance shown in the box. Now the Hydro Router exposes HTTP endpoints, which we can use with GET requests. So we're able to actually speak to the router dashboard itself using its own API. We'll see that shortly. Okay. So here we can ask the router for its version by typing v1 router version as an endpoint. We can see its health information via v1 router health. And we can see a list of available service instances via the v1 router list nodes endpoint. So we can also see API routes for all the related services. One thing we can do is actually speak with other services in the cluster through Hydro Router. Here I'm going to ask the asset service to return its health information. We can also do the same for the auth service. So we're seeing Hydro Router itself, a Hydro service, is able to monitor the presence of services running in the cluster. So let's kick this up a notch. At the top center, we see that we only have one instance of the auth service running. So let's go ahead and launch multiple or additional instances. First, we'll check to see how many instances are actually running. So we see there one of one. Next, we'll use the Docker service scale command to launch 2 more instances for a total of 3 instances. Give that a moment. Switching back to the dashboard, we see that we now have 3 instances of the auth service running. Zooming in, we can see that each instance has a unique instance ID. Now, we can call the health endpoint for the auth service. Let's zoom in first. Now we see if we refresh the page, we get back results from different instances. What's happening is the requests are being load balanced through Hydra. Now let's drop 2 of our auth instances to see what happens. We'll scale back to 1 auth instance. So we have 3 live ones now, and we're about to change that. We'll reissue the scale command, bring it back down to 1, so we lose 2. So switching back, we see that 2 of them have gone red, indicating that they're no longer present. And if we look closely, we see that the last remaining one starts with 82 and ends in 35 in terms of instance ID. That's going to be important for our next test. Keep that in mind. So it's the last surviving node. So let's try the health check again. Now we see that we get back responses from instances starting in 82 and ending in 35. We're getting, if we refresh the browser, we're only getting responses back from the only surviving instance, which means that Hydra is aware that the 2 instances are actually not present, they're not available. So it will not route to them. In fact, another interesting thing is that if it has trouble routing to a particular service, it can actually do retries. So you may never actually see a 503 service unavailable because it actually transparently did the rerouting, retrying. So let's zoom in a bit. So what we'll do now is we'll just tell the Hydra router to clear its endpoint. We can use v1 router clear to do that. And basically we'll clear the dead nodes. So that was presence and load balancing in action. Now let's try messaging. For this demo, we'll use the HMR service, which really just stands for Hydra Message Relay service. It basically will receive a response and send it back to the caller. Because this is a WebSocket test, we're going to launch a WebSocket client, just a Chrome-based one, and actually communicate to the HMR service through the Hydra router. So this is the WebSocket client. We'll issue a connect call. So we actually see the response back there at the bottom. The interesting bit, is, and we'll get to it, is basically the ID. What happens is when a new WebSocket connection is made to the Hydra router, it issues a client ID. The client ID is important because should the client need to reconnect, it can actually just use this prior ID and get back messages that were sent to it in its absence. So it's just sort of a recovery mode. So thing here is that Hydra router is taking WebSocket calls and transforming them into internal messages and routing them to microservices as pub/sub messages. Okay, cool. We'll step through that. So one last demo I'd like to share is the use of TCP dump to see the underlying Redis packets as they move between microservices. I'll issue a TCP dump command here, and shortly we'll see the packets. Yep, we'll start seeing them there. So we'll stop this in a bit. Okay. We can see various bits of TCP data, such as the sequence and length of packet. And we can see Redis commands such as setx and hsetx. So this is pretty interesting because you can actually see the cost and length and format of the Redis text protocol as it moves through. But a key takeaway here in these demos is that what you've seen is powered by Redis just at a much lower level. The last thing we'll do is tear down our cluster and continue this presentation. As you can see, Hydra is doing quite a bit with the help of Redis. Let's deep dive into Redis and see how it leverages. We'll deep dive into Redis and see how we're actually taking advantage of it. We won't cover all of the features here. Again, the full presentation is available if you're interested. Keep in mind that, again, that you don't need Hydra. Each of these features is made possible by Redis, and you can certainly do this in your own apps or preferred languages. What Hydra does do is automate and abstract the underlying details. That's something you should strive for if you build or use a similar library. As you know, each of these features can be addressed using various infrastructure tools. However, one key advantage in what I'll show you is that all of these features can be implemented just using Redis. As we'll see, Hydra makes extensive use of Redis commands and the Redis key space. Early on, it became clear that some thought needed to go into how to organize the Redis key space. Hydra's use of keys consists of names with 2 to 4 segment labels separated by a colon character. The segment labels are named prefix, service name, instance ID, and type. And for the most part, we try to keep this consistent, although there are a few places where it's not consistent, and we're hoping to address that in Hydra 2.0. The prefix segment allows for filtering Hydra versus non-Hydra keys. If you make heavy use of Redis, then being able to filter for specific keys is vital. The service name segment allows for filtering for a particular service type. Examples would be authorization, user, or image processing service. The instance ID segment allows for filtering keys by the unique service instance ID. When running microservices, you typically want multiple instances of a service type running. Each service instance is assigned a unique ID, and being able to differentiate between them is useful. Lastly, there's a type segment, which is used to classify the purpose of a key. Not all segments are present in each key. For example, service name and instance ID are not required in some keys. Here's an example of a key for the user service. We see the prefix, which is Hydra service, followed by service name. In this case, it's a user service. Next, we see the unique instance ID. And lastly, we see the type of this key is presence. So we say that presence information is stored at this key address. We can enter Redis CLI and type Redis commands to view various keys. We'll see examples of this throughout the remainder of the presentation. To recap, our use of keys in Redis is organized by segments, which makes them easier to query. Furthermore, a consistent organization makes them easy to extend and maintain. As we continue, we'll see the role that keys play in the organization of each microservice feature. Let's begin by examining presence. In the world of microservices, the ability to discover services and to know whether a service is healthy and can be routed to is of paramount importance. Many features depend on knowing that a particular service instance is actually present and available for use. This is also required for features like service discovery, routing, and load balancing. Once a second, Hydra updates the TTL time to live for a service key. Failure to do so within a 3-second period will result in the key expiring and the host app being perceived as unavailable. We can see here that the Redis commands used are get and setx, which sets the key and an expiration. We can query presence keys using the keys command with a pattern match. Notice that there are 3 keys present. This tells us that there are 3 instances of the asset service running. If we attempt to retrieve the contents of one of these keys, we just see that it contains the instance ID. Using the TTL command against the key shows us that this key has 2 remaining seconds before it expires. So not a whole lot of magic, just a whole lot of leverage of Redis. So to recap, microservice presence can be managed using keys which auto-expire. Updating the key is done automatically by Hydra on behalf of the host service, meaning it's not something the developer does. Failure to update a key within 3 seconds results in the service being perceived as unavailable. That means the service probably isn't healthy, which brings us to our next topic. Being able to monitor the health of a microservice is another important feature. Hydra gathers and writes health information snapshots every 5 seconds. You can check the snapshot for a quick view of an individual service instance's health. And the snapshots can be used by monitoring tools, such as the Hydra Router dashboard you saw earlier. So here's what the health key looks like. Notice that the only new bit is the type segment, identifying the key as being about being about health. When we view the contents of the key, we see that it contains stringified JSON. In this case, it's for the project service. Unstringifying the JSON makes it easier for us to see what's stored. It contains lots of useful information. So health information can be stored per service instance. It's managed using a string key that contains stringified JSON text, and that information can be used by monitoring apps. Next, let's consider service discovery, which is another must-have feature for any microservice architecture. The ability to discover IP and port location of any service by name greatly simplifies communication. Other bonus points include not having to manage DNS entries or create fixed routing rules. Service discovery information is stored in a Redis hash with a type of nodes. The use of a hash enables blazing fast lookups. We use the Redis hset, hget, and hgetAll commands to work with nodes with the nodes hash. The following Redis operation can be used to implement service discovery. The first is a lookup for a particular service type. The second is a lookup for available instances. The third lookup allows Hydra to retrieve information about a specific instance. We can see useful information such as the version of the service, the instance ID, the IP address and port, and finally the host name. In this example, the host name happens to be the Docker container ID. We can retrieve information about all available instances using the hgetAll command. This is how Hydra Router retrieves the list of services to show on its dashboard. Let's recap. Hydra queries using the service name key segment in order to discover various bits of information about a service. Service details can be managed using a Redis hash, which offers blazing fast service discovery. Next, let's consider routes. Routing both HTTP and messages such as WebSocket or PubSub requires that routes be validated. Microservices can publish their routes to Redis. And as an example, Hydra Router uses the published routes to implement dynamic service-aware routing. Each service publishes its routes to a key of type service routes. Here we see the key for the AdSet service routes. Service routes are stored in a set structure, a good fit, because you don't want duplicate route entries. The sadd and smembers commands are used. As an aside, Redis's rich collection of data structures is one of the reasons that what I'm sharing with you today is even possible. Returning back to our routes. We can pull a list of routes using a key pattern. Here we see routes for a number of services. We can use the smembers command to view the contents of a specific route set. By the way, the bracketed get, post, and put bits represent HTTP REST endpoints. For other messaging transports, the use of the bracketed methods may be omitted. So let's recap. Each service publishes its routes to a Redis set. Accessing the individual routes reveals a collection of route entries for that service. Routes are stored in Redis using a set data structure, which avoids duplicate routes. The published routes can be used to implement dynamic service-aware routing. Next, let's consider load balancing. As your application grows, you'll need to load balance requests among available service instances. This is accomplished with Redis using the service presence and routing features we've seen. At an application level, using Hydra, this is as simple as using the make API request or the send message call. Make API is HTTP, send message is PubSub. Load balancing takes place inside those calls as Hydra uses routing and presence information to choose among available target instances. A nice benefit is that during routing, if a request fails for a particular instance, Hydra is able to retry other available instances before returning an HTTP 503 server unavailable. As you can see here, load balancing relies on other features such as presence, service discovery, and routing. When presence is queried, individual service details can be retrieved. Here we see that for the AdSet service, we can obtain its IP address and port. So to recap, load balancing requests among services can be accomplished using presence, service discovery, and routing features we've seen. Redis strings, hashes, sets make this possible. Again, the whole is greater than the sum of its parts. Distributed services are forced to communicate with one another over the underlying network. HTTP REST calls are probably most common, but socket messaging can be much more efficient. Messaging in Hydra is accomplished using Redis PubSub channels, and Redis implements PubSub over socket connections. Here's an example key. Hydra uses the Redis subscribe, unsubscribe, and publish commands. As an aside, the Hydra router is able to accept messages over HTTP and WebSockets and convert them to PubSub. We saw that during our earlier demo. To understand how messaging works, Consider two services, the asset service and the project service. Each service creates two keys, one using the service name and another using its service name and instance ID. Each service listens to both channels. In most cases, you don't care which instance of a service handles a request. In those cases, the channel without a specific instance ID is used. Now, if you need to send a message to a specific instance, a channel with the instance ID would be the one you use. It's important to note that Hydra converts requests to a service name to one with a specific service ID instance when it load balances. That ensures that only one instance handles a given message or request. We can see a list of channels keys using the Redis pub/sub channels command. Notice that we have 4 keys here. The first key is the name of the asset service shared by all instances of the asset service. So you see the instance IDs are the only things that separate it. Next, we see 3 additional keys that show the unique IDs, one for each of the 3 instances. Continuing our focus on messaging, in order to ensure interoperability between microservices, it's essential to standardize on a shared format of communication. The universal message format is a documented JSON-based format which includes support for messaging, routing, and queuing. These messages can be stored in Redis as JSON stringified text. Here's an example UMF message. The to, from, and body fields are required, but services are free to include their own custom keys inside the body object. Let's see how this is used in practice. On the left, the client service sends a message to the project service. Note that this only requires the creation of the UMF message and then a send message call shown here in yellow. On the right, the project service listens for messages and processes them as necessary. That's accomplished using an event message listener. So one thing about Hydra is that Hydra derives from event emitter, so it itself is an emitter. Note that Hydra abstracts away the service discovery, load balancing, routing, and pub/sub specifics. Sending and receiving messages only involves 3 member functions. It's worth pausing here for a brief moment. Take a few seconds to consider what this example would look like using your favorite stack. Let's take a closer look. Send message works by parsing the to field to a message to determine the destination service name. With the service name in hand, the next step is to check for available instances. With the target instance in hand, the message is then stringified and sent via the Redis publish command. Again, we can list all the pub/sub channels in Redis. Messages can be sent via these channels and retrieved by listeners. So with this bit of programming, we're able to use Redis to route messages using a well-organized collection of channels. So in summary, it's worth noting that messaging is eventually necessary because services are physically distributed. Redis enables messaging using Redis pub/sub. And also standardizing communication is key. So we also saw how easy it is how easy communication can be when we abstract away the underlying service discovery, load balancing, routing, and pub/sub specifics. So that's just some of what's possible. And there's a lot more we could do. If you'd like to see a complete list, definitely check out the presentation on YouTube. In summary, what I've shared here is an approach that very heavily leverages Redis using JavaScript and Node.js. However, there's nothing preventing our friends who don't prefer JavaScript from doing the same with their favorite programming language. And because Hydra is open source, it can serve as a reference platform for such efforts. So that's how Hydra leverages Redis and how we were able to build our Fly Anywhere platform. So I'd like to show you how this all turned out. Here's a photo of the Bluetooth-enabled bike and metrics display. So a key call out here is that our microservices are dealing with real-time communication. Our bikes emit real-time data, which devices package into messages for transport via WebSockets. And Hydra Router routes them to their targeted microservices. We broadcast live from our production studio in Uptown. The studio utilizes state-of-the-art broadcasting equipment similar to what you'd find in a news station. However, unlike other studios, Ours runs a collection of microservices which support the automation of each live broadcast. So microservices power our production studio and serve customers via our AWS infrastructure. And we do all of this using lightweight microservices powered by Redis. We like to think this is all pretty badass. Trying something here. Still don't hear it. Okay. Yeah, so this is just another video. So I hope you enjoyed this presentation. If you're interested in applying these ideas or have questions, please feel free to reach out. Thanks for watching. Take some questions. Questions? No questions. Just questions. I know. I can feel it. So I have some questions. I mean, how many of you are actually using Redis or have experience with Redis? How much of this was clear from the Redis perspective, just kind of seeing the Redis commands and the CLI? Oh, pretty clear. Yeah. Yeah. Yes, good. We don't delete the data. So see, part of what Flywheel does, I mean, our secret sauce, our niche, if you will, if you compare us to SoulCycle and others, is that our key is to provide metrics to our customers. So if you take a SoulCycle class, they're not into metrics. Our writers absolutely care about metrics. They care about the stats. They care about results. They want to be able to measure those results, and so we store results going back from however long they've been a customer. So. Oh, no. So, yeah, Redis is largely a pass-through. We don't use Redis as a database. And so we are definitely moving data through. But we do move quite a bit of data through it to the point where we're looking at potentially separating a cluster out. And so Hydra will have its own cluster. And because Hydra doesn't really have that huge an impact on Redis itself, we can get away with a smaller Redis cluster compared to some of our other Redis use cases, sort of live video metrics, leaderboards, and things of that sort. Definitely more demanding. Yeah. Yeah. Just curious, how much does the bike cost? So the bike is competitively priced. No, it's about $1,600. You can see it on the Flywheel website. There's different models, so depending on whether you want the Android tablet on it or you want to actually use your own device, which is another, again, little innovation for us, is that we allow you to actually use your Android or your Android phone or tablet, your iOS devices, along with the bike, which is pretty neat. Yeah. All right. Okay, thank you. Thanks.
Yeah. All right. So, let's give it up one more time for all of our speakers. Thank you so much. Those were really, really awesome talks. Super excited to look more into Redis. And if anyone has any job openings they'd like to tell the community about, please feel free to come up and share a short blurb about where you work, what your position is you're trying to fill. Anyone have any job openings they want to come up and share? Ooh, nobody? Nobody's hiring in here? Damn, all right. Oh, man, where'd my mouse go? Well, thank you very much. I hope everyone enjoyed the talk today. If you haven't met, come up and say hello. Have a great night. See you next time.